Graphs of position versus time are a really useful way to model motion. In the previous video, we saw that they can lead to a great mathematical model because graphs can be represented by equations quite nicely. But for some problem-solving strategies, it might be nice to have something that's a little bit more like a picture of the actual motion itself. And this representation is called a motion map. A good way to get a quick feel for what a motion map consists of might be to watch this video I made with a toy engine a few years ago. So this is a toy train engine that we're seeing here.
In this video, in order to give you a feel for what a motion map is, I'm going to have you observe a real object moving while I make a motion map on this table. The object that I have is a small battery-operated train, and this train moves at a constant speed. I'm going to have a metronome ticking in the background that makes a ticking sound every 1 second. Watch what happens. As the train begins to move, I'm going to move one of these nickels in place to make a marker at the front of the train every second. What I've done there is I've created a record of where the train was at every second during the time it was moving. And that's the heart of a motion map. It's just a spot or a point that shows where it was every second. Now, I'm going to do more than that, and a good motion map should have more than that. It should have a velocity vector attached to each point so that we know relatively how fast it was going, and also we know what direction it was going. So I'm going to add some arrows, some vectors to my motion map. If I start at the first point, I know that it was moving in the direction toward the second arrow. So I'm going to draw that arrow. That vector represents the velocity of the train when it was at the first point. When it was at the second point, well, it was moving the same speed because this is a constant velocity vehicle. So I'm going to draw an arrow that's the same size towards the next point. I'm going to do it again. Because it's a constant speed train, the size of all these vectors should be the same. That's essentially what a motion map is. The train was actually still moving at the last point, and so I probably should draw another vector. I don't know if it fits on my screen, but it should be the same length because its velocity was the same. So the points are the positions, the vectors, the arrows, those represent the velocity. If the train weren't moving at constant speed, well, the arrows would be different lengths, and also the spots would be at different distances. But this is a constant velocity motion that you're seeing here. You'll notice that as I drew the arrows, I drew them from one point all the way to the other point. That was an easy way for me to make sure I was making my arrows the same length. And it does truly represent the velocity at some scale for the velocity vector size. Now, this can be applied to objects that you haven't seen move, and you can imagine where the points would be if a particle was moving at constant speed, or even if the speed was changing.
Motion maps all have some indication of the scale of position and the direction. Since this is one-dimensional motion, a simple number line will suffice to do this. So here we have a number line. You can see what direction is positive by where the arrow is pointing and which direction the numbers get bigger. So this represents position, and the position here is in meters, measured in meters. Then dots are placed along the scale that represent the position of the object at equal time intervals. Usually each second there's a dot, but there could be exceptions for different kinds of motion. It's helpful to know where the time starts, so usually at least the first second is given a label. For example, this object is moving forward, starting at 1 meter and moving at 3 meters every second, so the first dot we placed at 1 meter, and each dot after that would be 3 meters forward from the previous dot. So the first one's at 1, then 4, then 7, then 10. The last step in creating a good motion map is indicating the direction and size of the velocity at each second using a vector. So a vector is just an arrow, basically, that's used to model quantities like velocity that have both a size, which is modeled by the length, and a direction, which is modeled by which direction the arrow is pointing. In constant velocity motion, the vector lengths and directions will all be the same. A good way to make sure your vectors are good model is to extend each dot's vector to the next dot. In this example from above, the vectors would be 3 units long, representing a speed of 3 meters per second, and they're pointing forward, representing a positive displacement. Here are 3 additional pointers about making motion maps. If the velocity is negative, the velocity vectors simply point backwards. For example, the motion map for an object that started at 8 meters and had a velocity of negative 2 meters per second would look like this. Notice that a slower moving object has dots closer together on the motion map because it means the moves backwards in this case are less each second. If the velocity is 0, the object is not moving, we show that time continues to move or flow by stacking dots on top of each other in the same spot on the position scale with no velocity vector because there is no velocity. So for example, here we have an object that stayed stationary right at the position 5 meters for 3 seconds in a row by just stacking the dots on top of each other. And objects that do several different kinds of constant velocity motion, one after the other, can be modeled as well. For example, here's an object that went forward from position 0 at 4 meters per second for 2 seconds, and then it stopped for 3 seconds, and then it went backwards at 1 meter per second for 3 seconds. You could map it like this. So forward fast, stops, and then backward slow. So this gives you a tool to kind of give a realistic picture that's also got some mathematical basis to it for understanding how motion or modeling how motion occurs in constant velocity particle motion.